Hello everyone, my name is Kati Miettunen and I'm a professor in materials engineering at University of Turku. My research focuses on emerging solar cells, their materials, and also more recently energy systems. In this presentation, we are going to go through the motivation for solar energy research. Then we are going to look into sustainability of materials in solar cells. And third, we are going to look into recycling of solar cells. So first, let's go into the motivation for solar energy research. We get a lot of solar irradiation on the Earth, and the amount is actually 100,000 terawatt years annually that we get irradiation to the Earth. And if we compare that to the amount of energy required by mankind, that is roughly around 16 terawatt years. So we're looking at 10,000 times difference with the potential of solar energy compared to what is our consumption. Then if we go into deeper looking at what kind of other alternatives we have to fulfill our energy needs, we can see that solar energy is the only form of energy that can renewably fulfill and exceed the global energy demand. So if we look at the slide, we can see here the annual renewable capacity for various renewable energy sources, and we can see that most of them in their maximum capacity would be smaller than the annual energy use in the world. Then if we compare the energy use to the energy that the fossil sources could provide, we can see that there's limitations, because in this slide we can see the total capacity, not the annual renewable source, but the complete capacity, and it is relatively small compared to the world energy use at the moment. The surface area required to power the world is actually rather small because of the abundance of solar energy coming to the globe. And with these red dots, we can see the area that would be required for the global power production, utilizing solar energy as the only source of energy. Note also that we can utilize areas that are not suitable for agricultural use. Then again, we don't need to prepare solar energy in isolated locations around the world, but we can prepare it all around the world and prepare it where we need it. It has been argued that solar energy is the most evenly distributed natural resource in the world. If we, for instance, compare how much solar irradiation we get here in the Nordics, it's about half compared to the sunniest places in the world. And if we would, for instance, have half of the oil reserves of Norway, we would be very happy. So equally, we should appreciate the amount of solar irradiation that we have available, even in the Nordic countries. The other thing that we need to keep in mind when looking at the economic viability of solar energy is to realize that it's not only the amount of irradiation that is available, but also the local energy cost defines when solar energy is economically viable option. And for instance, in Western countries, electricity cost is fairly high, thus making solar energy economically more profitable compared to many more southern areas. So now we have covered that there's an abundance of capacity for solar energy. And next we're going to look at the use of sustainable materials in solar cells. I have been investigating the use of bio-based materials in solar cells, and those can be used in almost all components of emerging solar cell types. In this image, we will go through the operation of a conventional DI-solar cell. Here we can see that the sunlight is absorbed by a dye molecule, which is on top of the titanium dioxide network. When the dye converts photon into electricity, the electron transports through the titanium dioxide film to the conducting layer of the photoelectrode, where we have this conducting transparent oxide on top of typically glass substrate. The charge is then carried to the counterelectrode, where we have another conducting glass and catalyst, typically platinum catalyst, that helps transfer the charge from the counterelectrode to the liquid electrolyte, which then returns the charge back to the photoelectrode. So typically, emerging solar cells have three main components. They have the photoelectrode that absorbs the light, then they have the counterelectrode that returns the charge, and there's a medium in between that allows charge only to go one way. Next, let's look at how these components could be replaced with bio-based alternatives. So firstly, the commonly liquid electrolyte could be solidified by utilizing cellulose, gels, or membranes. These materials have also improved the efficiency of the device and also reduced the number of possible leakage pathways. The other option that we have is that we can replace both the platinum and the conducting oxide at the counterelectrode with biocarbon. The dye molecules that are used in DI-solar cells can be replaced with bio-based alternatives, and for instance, chlorophyll is a possibility. And lastly, we can utilize transparent paper or wood to replace the glass substrates in the device. So in this presentation, we will look into how to replace catalyst and the conductive layers with biocarbons, as well as how to replace glass with transparent paper and transparent wood. So let's first start with utilizing of biocarbons in solar cells. So this is a research that I started at Aalto University inside the FinCERES flagship, which is a collaboration with Aalto University and VTT. This research I'm also continuing here at University of Turku. The motivation for this work is that we should replace scarce and expensive materials used in counterelectrodes. For instance, platinum and indium in DI-solar cells and gold in perovskite solar cells. In this project, we prepared bio-based carbons utilizing low-value side streams or waste. In this project, we tested, for instance, brewery residues, and we are currently investigating utilization of wood bark as the biocarbon. The interesting fact with the biocarbon catalyst was that we could get much higher catalytic surface areas compared, for instance, to fossil-based carbons. So those were on average with this material 4 times higher compared to the fossil carbons. So when we look at the results, we could get equally high photocurrent with the biocarbon electrodes compared to the platinum. The only main difference was that the voltage with the biocarbon electrodes was slightly smaller compared to the platinum devices, and we're improving the electrode structure at the moment to reach similar performances. Then we go into looking at the other bio-based material, which is bio-based substrates for solar cells. So in this image, you can see a transparent paper made for solar cell purposes. You can see that it's not clearly transparent, but it does have a haze. And this is for a purpose that we will dig into later on. The motivation for utilizing cellulose substrates or wood-based substrates comes from the fact that glass contributes over 50% of the total embedded energy in solar cells, in these emerging solar cell types. So if we want to reduce the energy payback time of these devices, we should look at alternative substrate materials. The other fact is that glass is also extremely difficult to functionalize to get additional optical functions. This is because glass is prepared at high temperatures, and many advanced functional materials wouldn't survive the preparation process of the glass. Whereas cellulose is very good for all kinds of functionalization. The last thing is that the utilization of glass prevents combustion-based. The utilization of the glass prevents combustion-based recycling processes. And that is something that we should utilize to retrieve rare and expensive metals from solar cells. So let's then look at how these materials are made and how they boost the performance of the device. So when we would prepare transparent paper or transparent wood, let's take the transparent wood, we would first remove the lignin. So if you take a wood wafer, the brown parts in the wood come from the lignin. And when we have removed the lignin, we can infiltrate the remaining wafer with a polymer, resulting in a transparent material. The added benefit from utilizing transparent wood is that it scatters light in the forward direction. This in practice means that the light will travel a longer path inside the solar cell, which increases the light harvesting in the actual device. Here we can see existing literature studies where transparent paper was added on top of a solar cell, and it resulted in a significant improvement in the photocurrent. We have been now able to replicate these results, and we are also working on improving the photocurrent even further with additional functionalization. And lastly, we will look at the recycling of solar cells. It is so important to realize that not all critical materials in solar cells can be replaced with sustainable alternatives. For instance, silver has been very difficult to replace. That's why it's important to ensure that recycling takes place. It should be both technically feasible as well as economically profitable. In Western countries, it is sufficient that it would be technically feasible, but in particular looking at developing countries, economic profitability is critical to get the recycling of solar cells to realization. So when we are developing new materials and new solar cell types, it is critical to utilize recycling as one of the guidelines for developing new materials. The reason why it is not that at the moment is that the issue of recycling is complex in multi-material devices such as solar cells. The proportions of materials as well as the combination of materials defines if materials can be recycled from the system. So in this slide, I show our recent unpublished results, where we can see that materials basically fall into 4 different categories. Materials that could be retrieved with conventional recycling methods, materials that are unrecoverable and would be lost, and those are the important materials that are rare and or expensive. So the third category are materials that would be unrecoverable, but those are abundant. For instance, bio-based carbons fall into such category. Those are from renewable sources, and we don't need to focus on retrieving them. Then the fourth category are hazardous materials that, for instance, form toxic gases in the conventional recycling process. So when we look at what is the conventional state-of-the-art of emerging solar cells, we can see that all the materials fall into the categories that they would be, it would be impossible to recover them, and we also lose expensive and rare materials, as well as are faced with materials that form toxic gases in the processing. But even with a simple change in the system, for instance, changing from a very thick glass that is conventionally used to, for instance, thin flexible glass, and choosing different materials options for different components, we arrive to the situation where all expensive materials could be retrieved and only abundant materials would be lost. So the take-home message is that firstly, the potential of solar energy is massive both globally and locally. Bio-based materials could be used to serve as sustainable and even performance improving alternatives, and in particular for emerging photovoltaics. And then thirdly, recycling of solar cells should be guiding materials research, in particular in emerging photovoltaics research. Thank you.